Welcome back. Today we're going to start chapter 7. First section is integration by part. Sometimes we cannot solve certain integrals through substitution or simple integration, though there is another method or technique to solve that specific integration. And that is what we call integration by part. The idea starts from the product rule. Let's say if you have two functions f and g multiply by each other, and I ask you to find the derivative. We know the derivative should be f times g prime plus f prime times g. So now if we integrate both sides, that means the integral of all these would be simply these two are inverses of each other. You take a derivative and then you integrate. That means originally this must be f times g, because the integration and the derivatives are opposite operation of each other. And on the other side, what we have is the integral f times g prime plus integral f prime times g. So sometimes what you're given is one of these two integration. For example, you're given integral of f times g prime, and what you can find is simply this integral f times g prime would be f times g minus the other integration, which is f prime times g. Another way to write it is, instead of f, you can use the variable u, and g prime dx could be shown by the derivative with respect to variable x into the function v. You assume u and v are both functions, then what you have is the function u times the derivative of the function v. The integral of that would be simply u, v, the product of the two functions, minus the integral of the function v multiplied by the derivative of the function u. This second one is the common notation that we would use. We don't use f and g because sometimes there is the function f given and the function g is given. So we avoid that when we use u and v. Okay, so if it's required to use substitution, maybe instead of u, sometimes you have to use substitution as well as integration by part in examples. I'll show you examples later, but if it's required, maybe choose substitution. Instead of using u, use a different name. Use t, z, whatever other variable is. Okay, so let's call this substitution. Maybe this method, integration by part, to use the second. We often use this second method. How do we use it? Let's look at this first example. Let's say given the integral of x times sine x dx, and they ask you to find this integral. If you use substitution, if you would have said, okay, let's pick x to be, or sine x to be t, then you cannot get rid of this x, because the derivative of sine x would be cosine x, and it doesn't help. So what we can do is we try to use this technique. If the substitution method works, use substitution. But in this case, the substitution wouldn't work because the derivative of sine would not show up and this x would not cancel out. So if you try it, you'll notice that this substitution wouldn't work here. But the idea is, it looks like a product of two functions. One is a polynomial, the other one is trigonometric. Most of the time in these cases, the integration by part is the technique. So what we do is, we say, let's call x be our function u. And the choice that you make to pick which one to be the function u, which one to be the function v, is normally you pick the polynomials to be the function u, because you want to get rid of that function. And every time you take a derivative, the degree of the polynomial will reduce. And we pick the trigonometric function to be our dv. So in this case, I'll pick x to be u, and I'll pick sine x dx equal dv. I have to pick the dx because this is supposed to represent the derivative. So sine x dx, we call it dv, and x we call it du. What we need is, we know we need to find out what is u. We already know what u is. We need to figure out what is v. We don't know what v is. We know dv. So how do we find v? V basically would be the integral of dv. So v is the integral of both sides, because the derivative of v is given. If you want to find v, you just need to take an integration. So if we integrate sine x dv, what we get is, what is the integral of sine x? It was negative cosine x. So this would be negative cosine x. And on the other side, what we have is simply v. Right? The derivative of cosine would have been negative sine, so the integral of sine would be negative cosine. This is our v. And then we found v, so we know these. What we need to figure out now is what is du. So u is given. What would be du? Du would be derivative of x, simply dx. 1 dx if you want. Okay, since we know these, now I can answer the question. What is the integral of u times dv? It is u times v. U is x times v, which is, we found, negative cosine x, plus, sorry, minus, this is uv, by the way. Maybe use parentheses for the minus. This is u times v. Minus the integral of v times du. V is negative cosine x times du, simply 1 dx. 1 dx. So this integral is basically, I'm going to multiply this, is negative x cosine x. Negative would be plus integral of cosine x dx. Now the good thing about this is now I can answer what is this integral, because it's simple cosine and it doesn't require any substitution or anything. So I can say this is negative x cosine x plus the integral of cosine. This one's supposed to be easy, sine x plus some constant c. Okay, this is the integral of the x sine x. You can check. How do we check? This is, so if we're trying to check to see if this is the correct integral, we take a derivative of negative x cosine x plus sine x plus c. If we take a derivative of that, let me write d over dx. Whatever we get should match here, should match with x sine x. So what do we do derivative? Derivative of negative x cosine x, I should use product rule. It would be negative x prime times cosine x plus negative x times cosine x derivative plus derivative of sine x is simply cosine x. The derivative of constant c would disappear, plus 0. So here what we get is negative times negative x derivative would be negative 1, so negative cosine x plus derivative of negative x cosine x would be negative x times derivative of cosine x is negative sine x. So plus cosine x. And what we notice is here is that these two will cancel out and negative times negative becomes positive, which is x sine x. So we figured out that the integral of x sine x is basically this term, and it is correct since we checked it. You don't need to always check, but I just wanted to show you that there is a product rule involved. And the idea of this product rule is basically how we get this integration by part technique. Okay, let's do another example. Let's look at this example. ln x dx. Here, if you pick substitution again, if you pick substitution and say u equals ln x, let me show you this. I will erase it, but let's say you pick this and say, okay, du now would be 1 over x, d over dx. So therefore, du equals, du divided by, so therefore x times du equals dx. Then if you go back to the integral and substitute, ln, we call the du, dx, now it's x times du. Now here, you cannot simplify this anymore because you have two variables and you cannot get rid of x. So the substitution technique wouldn't work here. So that's why the integration by part may answer this question. So first, you have to figure out what are the functions. one of the functions we can see, it is ln x. But we don't see the second function. The second function is simply dx. That's our second function. So this, what we call it, du, and the other one would be dv. So I will say u equals ln x and dx equals dv, or dv equals dx. So then I can find out, since I know that I need the derivatives, I find out what is du. Actually I should say du divided by dx, or you can write the dx on the other side. Sorry about that. In the last example I forgot to write dx here. Derivative of, oh no, I wrote it, 1 dx here. Derivative of ln x is 1 over x, but this is supposed to be du divided by dx, so I multiplied it. I kind of fast-tracked it in the last example. We can multiply that dx and write it on the other side. So the derivative of u equals 1 over x, the derivative of ln x, which is 1 over x, and dx. The integral on the other side, the integral of dv will give us v. The integral of dx would be simply x, right? The integral, this is 1. You can say the integral of 1 would be x. Okay, so now that we know u and v, I can replace it, say, the method of substitution. The integration by part was integral of u, v is u times v minus v times du. So I have u and v, so it would be ln x multiplied by x minus integral of v, which is simply x times the du. Du is 1 over x dx. And x times ln x, it would be x ln x minus the integral of x times 1 over x. These two can cancel out. What is the integral of 1? It's simply x plus some constancy. And this would be our result. It doesn't have any integration. And you see, you can write this answer maybe in a couple of lines. Not always is this easy, but if you pick this ln to be dv, for example, if you pick dv to be ln x dx, then there is no way to solve this integration because you do not know the integral. So the choice of picking u or dv is kind of important too. You can check this as well to see. I'm going to check this one as well just to make sure that we know the idea. And you notice that every time you check this integration by part, you always have product rule involved, because you have two functions. X times ln x derivative would be x derivatives times ln x plus x times ln x derivative. And on the other side, you have minus x derivative plus c derivative. I could have answered those, but I wanted to do everything in one step. The derivative of x would be simply 1, so we have 1 times ln x, plus the derivative of ln x is 1 over x, so we have x times 1 over x, and minus the derivative of x is simply 1, plus the derivative of c, 0. These two can cancel out, so you have 1 minus 1, so this will cancel out, and 0 is gone, so what we found is just ln x, and that's what we had originally. We tried to find the integral of ln x. Okay, so this was our result. You don't need to check your solution, but it's good to make sure that your answer is correct. Here's another one. Integral of t squared e to the t dt. So what do you pick as substitution? If you, again, another substitution as a part for the integration by part, you pick u to be most of the time to be the polynomial. So I'll pick u to be t squared. And I'll pick dv to equal e to the t dt. So now I can answer, what is du? Du would be 2t. This is supposed to be du divided by t. I multiply the dt to the other side. What is v? If you integrate both sides, the integral of dv would be v. Integral of e to the t dt. The integral of et is simply e to the t. So now I have u and dv. Sorry, I should have chosen a red color. So here you can say u times v would be t squared times e to the power t minus the integral of v times du. So v is e to the t, du is 2t dt. Okay, let me rearrange this. I have t squared e to the t minus, you can put them in order again, 2t e to the t dt. Okay, you may notice that it's not easy to calculate this integral either. So what you can do is you can try integration by part again, because from here the degree of the polynomial reduced from t squared to t. This is t to the power 1. So if we do it one more time, that t will disappear. So what I'm going to do is I'm going to try again substitution, not substitution, integration by part. Let's use a different color. Sorry about that. Let's pick black. So here I'll pick, we're done with that integration by part. Let's continue. I'll pick the new u to be 2t, and I'll pick dv again to be e to the t dt. It's like taking a derivative, taking integral again. So if you do substitution once and the question simplifies and you need one more substitution, you will do another substitution. The same with integration by part. If it requires another integration by part, you will do that again. So du would be, the derivative on both sides would be 2 times dt. Derivative on the integral of dv would be v. The integral of e to the t dt, simply e to the t. So this, now this equality t squared e to the t is still there. Minus, here's the important part. Whatever you write here, that negative sign should be distributed to it. Okay. So now here we apply the integration by part. Again, u times v, it would be 2t times e to the power t. This is u times v, product of these two, minus the integral of v times du. V times du, these two. It would be 2 e to the t dt. I put them in order. It's supposed to be 2t times e to the t, but I write the dt at the end. Okay, so this equals to t squared e to the t minus 2t e to the t plus, negative times negative becomes plus, 2 e to the t dt. Okay, the good thing at this point, you notice that the t squared kind of reduced to simple 2. And 2, you can write it outside the integral because it's a constant. So you can write it as 2 integral of e to the t dt. And we can answer that. This t squared e to the t minus 2t e to the t. The integral of e to the t is still e to the t. So you have plus 2 e to the t plus some constants. And this is the answer to this question. You notice that it required 2 integrations because we had to do this integration by part twice. It's last time we talked about the Hospital rule. Sometimes when you take the derivative, you still have indeterminate form and we need to do another one. This is similar idea. You have to do the integration by part twice. Okay, so you try to check to see if this is the correct integration by part. The result is correct. If you take a derivative of this, you're supposed to get t squared e to the t. Okay, so we didn't do anything with boundary, so here's another example that you only have one function, and that function is tangent inverse of x. In the cases when you only see one function, normally substitution wouldn't work, because tangent inverse of x, if you pick substitution to be called to u, then an x will show up by taking the derivative. There would be another x. You would have both u and x in the integration, which is not kind of easy to solve. So what we can do is you can try this integration technique. So what I'm going to pick, I'll set the u to be t tangent inverse of x, and we'll pick dv, similar to the last the example above, not this one, the one before that, take dv to equal dx. The boundaries doesn't really matter because we can always evaluate at the end. So what I'm going to do is I'm going to wait till the end and I will evaluate. So assume that there is no boundary at the end, we will implement these boundaries. So du, derivative of tangent, it's 1 over 1 plus x squared, and du divided by dx if you multiply dx to both sides. So here we would have that. The integral of dv would be v, the integral of dx it is x. So what you do always here is the integration. You integrate, and from this step to the next one, we take a derivative or differentiate. Okay. We need to find out what is du, and the other side we need to find out what is v. The derivative is given, we need to find out the original function. In this one, the original function is given and we need to find out what is the derivative. So I can write this integral. Yeah, let me write the next line. It's equals to, okay, so 0 to 1 tan inverse of x dx equals u times v again, which is x times tan inverse of x minus the integral of v du, which is x times 1 over 1 plus x squared dx. Okay, so here we can notice that there's supposed to be these boundaries somewhere that need to show up. I'm gonna wait till the end, but in some of the books, in most of the books, they evaluate here. They say from 0 to 1 and from 0 to 1. This is how it's supposed to be. But you can wait till the end and then evaluate the boundaries. Yeah, either way is fine. So I'm gonna wait till the end and then evaluate. Okay, so let's say we already know this part, x tan inverse of x from 0 to 1 minus the integral of, let me write this again, 0 to 1 x times 1 divided by 1 plus x squared dx. Here's the good thing about this part. You don't need to do integration by part again. What you can do is simply, you can use substitution for this one, for the second part, and figure out what is the answer. Because substitution in this second integral simply helps us. The derivative of the denominator would show up in the numerator. It would have 1 plus x squared derivative, which would be 2x. So what I'm gonna do is I'm gonna do a substitution. In this case, I'll pick the substitution and I'll call it t, for example. I'll say t, let's call it to be 1 plus x squared. Then what is dt? dt would be, sorry, we need to figure out what is dx, so we take a derivative. It would be 2x, this is dt divided by dx. So therefore, dt divided by 2x would be dx. Okay, so the integral, again, this is still there, x times tan inverse of x evaluated from 0 to 1 minus the integral of u, have an x divided by u from 0 to 1, and instead of dx we can replace dt, sorry, not u, we call it t, dt divided by 2x. Okay, let's continue. I should create more space here. Push this a bit down. Sorry. Move this down. Okay. So this x's will cancel out. You notice now we have only one variable, and that is t. So this would become x times tan inverse of x evaluated from 0 to 1 minus, that's why I didn't want to write this 0 to 1, because every time you have to rewrite this and evaluate, or at the end you can evaluate. You could have evaluated the beginning as well. Minus the integral of 1 over t times dt over 2, which you can write the 1/2 or the 2 outside as 1/2. Now the good thing about this integral is that we know, by the way, the boundaries are not supposed to be 0 and 1 because we've done substitution. So let's ignore the boundary at the moment. We'll go back and replace it. So now integral of 1 over t is simply ln t. So this would be x tan inverse of x evaluated from 0 to 1 minus 1/2 ln t. And there is no constant c required because we know there is boundary. So this would be x times tan inverse of x times minus 1/2 ln. Instead of t, I'll replace it back with 1 plus x squared. And then let's evaluate from 0 to 1. So if you would have ignored that it's evaluating till the end, that would have been fine, but you'd always mention that there is you need to evaluate at the end over the boundary. Okay, let's evaluate. Replace 1. You'll have 1 times tan inverse of 1 minus 1/2 ln of 1 plus 1 squared minus, this is if we replace 1. If we replace 0, what we get is 0 times tan inverse of 0 minus 1/2 ln of 1 plus 0 squared. Okay, some of these are simple numbers you should be able to answer. Here, tan inverse of 1, at what point tangent, at what angle tangent equals to 1? This is pi over 4 at 45-degree angle. ln of 2, this is ln of 2. We don't know what ln of 2 is, so I'm going to leave it as that. 0 times tan inverse of 0, that will disappear. ln of 1, this is 1 inside, ln of 1 is simply 0. So this side would be 0 times 1/2 as well, this is gone. So what do we get at the end is 1 times pi over 4, which is pi over 4, minus 1/2 ln 2. Without doing integration by part, we wouldn't have been able to find this. And it's not easy to guess this result because it both involves logarithmic and the inverse of trigonometric value. Okay, so this was an example where you have boundaries. So without the boundaries, it's easy. With the boundaries, you have to be careful at the end, or you could have calculated this right here and say this would have been pi over 4. So every time you would go to the next step, you would write pi over 4 minus that integral. And you wouldn't need to evaluate. But most of the time, I will keep it till the end, just to make sure that all the steps are written. Okay, here, let's look at the next example. Cosine ln x dx. I chose these examples because each one has specific information. In the first example, it was simply to be familiar with this idea of integration by parts. Second example was to see if you have one function only, what do you do? In the third example, I showed that you need to integrate by part twice, multiple times. In the fourth one, we had boundaries. Now in the last one, I'm going to tell you that here, you can't start with integration by part. Integration by part here doesn't work by itself. Because you do not have, if you pick this function, this is one function because there is no product. This is cosine times ln x. If you pick this function as you would be able to calculate, but it's kind of needs substitution at some point. So what we can do is first we can use the substitution. Let me write the question better. Sorry about that. So the question is integral cosine of ln x. So ln is an input to the function. So normally in this case, what you do is you pick substitution, right? We say, okay, let's call ln x be our substitution, call it t. So dt would be simply the derivative of ln x is 1 over x, and multiply both sides by dx, you'll get this. So I can write this integral as cosine, and here dx would be x times dt. So this would be cosine t times x dt. Right? Notice that the substitution doesn't really help, because cosine t times x times dt, there is an x, there is an t. So what you can do here is you can find out what is x. You can find out what is x. Using this integration by part, this substitution, I can find out what is x. X would be raise both sides to the power e. This way I can get rid of the x in the integral. So x would be simply e to the power t. So I can replace x and say this is equal to cosine t e to the power t dt. Because x should be replaced by e to the power t. You notice the substitution by itself didn't give you only t, so you had to create this tactic to get rid of that x somehow. If you do integration by part, there's a chance that this will work as well. I'm going to try it later at the end to see if we get the result, but I feel like this would be kind of complicated. So let's try this. Okay, create some space first. Okay, so here, what do we pick for our integration by part? We let u equals cosine of t, and we pick v to be e to the power t dt. Sorry, dv. So therefore du would be negative sine t dt, and v would be e to the power t. The integral of e to the power t dt is still the same. So this would equal u times v, which is negative sine cosine t times e to the power t minus the integral of negative sine t times e to the power t dt. Here's the good news. The good news is the integration of the good news is that the integrals of e to the power t and the derivative of cosine is easy to figure out. So this would be simply integral sine t e to the power t. The bad news is when there is product here, you cannot calculate this integral simply. It's the same question as if I asked you here, cosine t e to the power t. So maybe another integration by part will help. So let's try another one. Let's do it one more time. Again, I'm going to call this u. In this case, in the second integral, I'm going to let u equal sine t. And on the right side, I'm going to pick dv equal e to the power t dt. So du would be cosine t, dv, v would be e to the power. So now this equals to cosine t e to the power t is still there, plus, so this integral, we're doing integration by part again. So the product of u and v, which is sine t times e to the power t, minus the integral of, we multiply v by du, what we get is cosine t e to the power t dt. Okay, you notice we started from here and we ended up at the same thing. So it didn't really help us, this integration by part. Or did it? So let me show you the idea here before I tell you. So let's say if you know let's say you're solving I. I is a variable, or let's call it y or something. And y is given 2 plus x plus y. Sorry, minus y. And if you're solving for y, you can simply move this to the other side if there is an equality and say, okay, 2y equals 2 plus x. Therefore, y would be 2 plus x divided by 2, right? This would be very easy. So here, if you look at where we started, if you look here, we started with integral of cosine t e to the power t dt. So what we have here, I'm going to write the integral of cosine t e to the power t dt. And we figured out at the end this equals to cosine t e to the power t plus sine t e to the power t minus integral of cosine t e to the power t dt. Right? This is where we ended up with. We know these two are equal to each other through integration by part. So if I'm looking for this integral, I see exactly the same thing on the other side. So if I move this to the other side, what do I get is two of them. You add this integral to both sides, you get two of these integrals, 2 cosine t e to the power t dt, 2 cosine t e to the power t dt. On the right side, what do you have is cosine t e to the power t plus sine t e to the power t. So therefore, now I can figure out what is the integral of cosine t e to the power t dt. Is exactly that divided by 2 plus sine t e to the power t divided by 2. This is a common technique when you're dealing with product of trigonometric function and the exponential. Normally, after you do the integration by part twice, you will end up with the same term. This is very common. So if you're dealing with the product of polynomial and trigonometric function or exponential function, pick the polynomial to be u. If you're dealing with product of trigonometric function and exponential, if you do the integration by part twice, then you will go back to the same term. And the technique is always to do this. Write them equal to each other, solve for that integral, and at the end, you can figure out what is the integral by itself. So we figure out this is the integral. Okay. By the way, there should be a plus constant c at the end, because this integral involves constant. You should add a constant because we integrated these terms. But the integral always involves a constant. Okay, so here, the constant divided by 2 doesn't require anything. So here, what you need to know is that we're not done, because here everything is in terms of t. What we started with, what we call t to be ln x. So you have to replace all those t's with the ln x and say, okay, I can answer the original question. That was cosine of ln x dx. What was the integral? What was the answer? Cosine of ln x dx. We ended up with integral of cosine t dt, integral of cosine e to the power t. So at the end, we end up with this result. Cosine t e to the power t plus sine t e to the power t divided by 2. Sorry, instead of e, I forgot to replace the t. You should have cosine ln x times e to the power ln x plus sine ln x e to the power ln x divided by 2 plus some constant. The good thing is that you can answer this too. What is e to the power ln x? It's a composition of e and log ln. So this is simply x. So you would have cosine ln x times x plus sine ln x times x all divided by 2 plus some constant. And this is our integral. as a test, just try to check to see if the integration is correct by doing a what do they call it? By doing a, if you do integration by taking a derivative. Sorry about that. Okay, so try to take a derivative to see if the result is correct or not. Okay, I mentioned that I will try to do this by integration by part as well, originally without the substitution. So let's do that. Let's say if the question was originally given cosine ln x dx, and we want to find out this integral. If you do, if you pick u to be cosine ln x and pick dx to be what is dx? Dx to be dv, so dv equal to dx. Then the derivative of u, du, requires what does the derivative of u require? It requires a chain rule. Derivative of cosine, which is negative sine at ln x, multiplied by the derivative of ln x, which is 1 over x. On the other side, we have the integral of v, which is integral of dv, which is v, integral of dx, which is simply x. So what we get is u times v, which is x times negative sine ln x. This would be equal to x times negative sine ln x times 1 over x minus the integral of v du. So v times, this is x times cosine ln x. I wrote it incorrectly. And for the other one, we get v times du, which is negative sine ln x times 1 over x times x dx. Here's the dx here. And here these two will cancel out. So what we get is x times cosine ln x minus minus would become plus integral of sine ln x dx. Again, you notice something. You notice that we started with cosine ln x, and where did we end up with is integral of sine ln x, which means there is a similarity between these two. So it means if you apply the integration by part again, you would probably end up with cosine ln x somewhere. So let's do that again. So I'll say u equals sine ln x. I'm trying to calculate this integral. And then dv, I call it to be dx. The derivative of u would be, again, chain rule, derivative of sine is cosine, evaluated as ln x, multiplied by the derivative of ln x, which is 1 over x dx. On the other side, the integral of dv is simply v, and v equals to x. So what do we have here? We have the integral of sine ln x could be replaced by cosine ln x. The integral of sine ln x could be replaced by u times v, which is x sine ln x, minus the integral of v times du. v times du, the x's can cancel out when you multiply, so you would end up with negative cosine ln x cosine ln x d. Okay, as I said, here is the two terms equal to each other. Same thing. So you can kind of add cosine ln x to both sides of the equality, the integral of cosine ln x to both sides of the equality. And what you would get is 2 integral of cosine ln x dx would equal to x times cosine ln x plus x times sine ln x. And if I divide both sides by 2, this 2 will disappear and it will show up in the denominator. And plus some constants. Okay. It turned out that we didn't really need it, that we didn't need this substitution. I thought without the substitution it won't work, but it's nice that without the substitution it's easier. So this would be our answer, which is exactly the same as what we got above. So sometimes you need to do substitution, and this was not a good example that I picked. Maybe another one. Not always substitution is required, but if you see the question is super complicated, maybe you can break it down by choosing substitution if you're dealing with composition of functions. In this case, I saw composition of function and I thought, okay, substitution would be a good idea to start with. But at least now you see two different examples. One is if you start with cosine t e to the power t, then you need to do this integration twice, integration by part. If you start with cosine ln x, it turns out that you need to do the integration twice. Okay, so this is it for this section. Try a bunch of examples. They are very similar to these ideas. Not always it's required to do integration by part, but if the substitution or the simple integration doesn't work, then maybe the choice is supposed to be integration by part. And again, not always integration by part would work either. So something like maybe x to the power 2 e to the power x cosine x. Maybe here you need more than integration by part. Maybe for this example. Not sure. You have to spend time think about, okay, which one would work, which one doesn't work. So in this case, maybe try to see if you can figure out what is this integral. I'm not sure that it's that easy. Cosine x, e to the power x. Cosine. Okay, maybe pick this to be dv and this one to be u. There's a chance that it will work out, but it requires multiple integration by part. Okay, so I'm gonna stop here.